Hello friends, good morning and good evening everyone. Your ALP here again. So in this video we are going to discuss 370 watt single phase induction motor design. Yeah, before going to the design, let's discuss a general way. So why we are discussing all these designs? Earlier I discussed DC motor design and then the induction motor design. I made a alternator video also. I didn't post it that. I will do it. And CT design also we discussed. Now we are with a single phase induction motor design. Why all these things? Because these AC machines uh, and DC machines plays a major role for translating the electrical energy into the mechanical energy, mechanical rotational energy. Mainly e-vehicles, electric vehicles is going to play a major role in coming days. So in electric vehicles, so the motor plays a major role for operation. So what motor is required, DC motor or AC motor? Because we are going to store in battery the electrical energy, that will be obviously in DC form. So what is best way to utilize that DC energy? What is the good way? So that's what our designers choice. So one way is simply used in DC itself, simply discharge it and use it. That is one way, but that may not be suitable most of the cases. So we need to regulate that DC itself. We can use a chopper, DC chopper, or some other power electronics circuit for the maintaining proper values, voltage and current levels. That is one thing. Otherwise, simply convert into AC of very high frequency, so that the machine size will be low and all the equipment size will be low, high frequency, and use any other AC machines. That is one thing. So this is the basic the things that those were involved in this electric vehicle. So after going through all these designs, finally we are going to choose one design, and we are going to make different machines for that particular design. Say for example, if it is a 5 kilowatt motor, for the 5 kilowatt motor we are going to do DC motor, we are going to do AC motor, we are going to do 3 phase motor, we are going to do single phase motor, and various advantages, disadvantages with each design we are going to discuss. So this is very the long run. I mean, maybe in 2 to 3 months we are going to plan that, but as of now we are just discussing this induction motor design, single phase induction motor design. So what is the problem here? So in this case you can just observe here. So design a 370 watt 230 volts 50 hertz 4 pole single phase capacitor start induction motor. So this induction single phase motors are not self starting, they need some starting other means. So we are using capacitor here for starting this motor. The full load efficiency of and power factor is so 0.65 and 0.62, and the starting start should be almost 300% of a full load torque, because for starting the machine we need more torque, because it is standstill, right? More inertia will be there. So, and you should not draw more current from the circuit, otherwise the circuit, I mean the fuses and everything will blown off, fire also may happen. So maximum current we should restrict ourselves to 21 ampere. So the motor is to be open type with a temperature rise of windings not above 40 degrees centigrade for continuous operation. Yeah, this is the problem, guys. So this is a simple, very clear cut problem. So we have to design this motor, single phase induction motor. Yeah, so let's summarize this again. Specification. So whatever you are watching, this green color one, that is the stator, and it has some slots in it, and this is our entire motor is of 370 watt capacity, and the efficiency should be more than 0.65, power factor should be more than 0.62, and we applied 230 volts supply of 50 hertz here, you can see it here, and this is of capacitor, so that's why I drawn capacitor here. So the starting torque should be 300% of full load, and starting current should be less than or equal to 21 amperes, and winding rise should be 40 degrees centigrade. for a continuous operation. Yeah, this is the problem and this is the specification we have. So let's begin the design. Let's be with me till the end so that you can get better understanding. If you have any questions or doubts or anything, you can post in comment section so that I can reply you. Yeah, my details are available in the description. You can revert to me. Yeah. Before that, here you have n equal to 120 f by p. This is the RPM, rotations per minute. This is the basic formula. We will use 120 into 50 hertz by number of poles. So let's calculate. This is the basic table here. For example, if it is a 2-pole machine, then if 50 hertz, then we will have 3000 RPM, 1500 RPM, 1000 RPM, 750 RPM. So this is the table we have up to 20 pole. So for 20 pole machine, this is of 300 RPM. So for 50 hertz and 360 RPM for 60. This is the template for different speeds versus poles combination. So here you have, for example, actual speed in this case is 1430 RPM. So let's choose the nearest RPM we have is 1500 RPM for 50 hertz and for this 4-pole machine. So this is the actual speed. So nearest synchronous speed is 1500 RPM. So let's calculate RPS, synchronous speed in RP rotations per second. We will say small ns, 1500 by 60, that will be 25. So let's calculate number of poles now. Number of poles will be 4 in this case. So we are going to calculate one figure here, one factor, we will say ratio, that is output by speed. So for 370 watts output, if it is rotating at 25 RPS, then the factor is 14.8. So kVA input, we have some basic formula. I mean, I am just deriving one formula here. That is Q is nothing but C naught D square L into Ns. So let's calculate D square L, Q by C naught Ns. So here C naught is nothing but 11 kW B average AC into 10 power minus 3. This is the basic formula we have. If rating of machine is given in horsepower, so we should consider Q as horsepower into 0.746 by efficiency into cos phi. So let's substitute everything in D square L. D square L equal to HP into 0.746 by eta cos phi C naught Ns. So this is the thing. So we have one table here. So table 2. So in this table, watts per RPS, if it is 3.6, the factor is 9.5, 7.2 means 12, 12 means 15.5, 18 means 18. This is one table we have. So from that table, the C naught efficiency cos phi, that value we got it as 16.5. So D square L is nothing but, let's calculate this. We know 0.37, just substitute 16.5, RPS is 25. So we got this value. So let's take length by the pole pitch tau as 1. So we can get D as 0.1045 meter, that is 4.11 inch. And we have one table here. This is the standard table for stator outside and inside and number of slots. Similar way for rotor also, outside, inside and number of slots and approximate weight also per lamination also it is given here. So let's consider this table and process this. So we got here 4.11. So in this table, almost closer one is this one, 161M. This is the closer one. So we chosen this. So for this 4.3 is the inside dia and 7.77 1 by 8 inch. Everything will be in imperial units in inches. This is outer dia. We have 36 slots in the rotor, I mean in the stator, and rotor is also similar way. We just ignored the air gap here, but of course air gap is there. That will be very small, 0.5 mm, something like that. So for consideration, we just took same value rotor also. Here inside dia is 1 by 8 and we have more slots here in the rotor, 44 slots. So 36 and 44 are the slots now. So 14 is the weight. So from this table it is chosen the 4.3 inch stator, inner diameter and inner dia 161 mm, that is the model now. So length of core, what is the length of core? What is the stator bore? 4.3 is nothing but 109 mm if we convert into the mm. So just substitute in the above equation. L is nothing but 75 mm. So we got 109 mm diameter of stator, and this is of 75 mm length. So this is very small motor, DC motor. Yeah, we have some standard template for that stator laminations also. You can see it here. The entire stator is a 0.75 inch height and a 0.15 inch width, and 4.3 is the diameter. So yeah, this is what the details. So in mainly in small machines, the consideration, the approach is different when compared to the bigger machine. In bigger motors, where it will be in, for example, 100 kilowatt, some very high rating kilowatt range motors, where we will start everything with D and L. D we will calculate, L we will calculate everything. We don't follow the standard template there. But here, calculation of slots and all is very difficult. I mean, up to D and L is okay. After that, we can't calculate small slot dimensions. It is very difficult. So what we will use is, we just chosen one standard available to nearest the frame, motor frame, stator frame and rotor frame. And what we are going to do is, based on our rating, for example 370 watts, how much current is there, so how many turns required, so whether we are able to provide the number of turns and the conductor cross section in the slot or not. That's what we are going to check it. That's what we should do for the smaller machines. So let's calculate pole pitch here. Yeah, that is tau is nothing but pi into diameter by number of poles, pi into 109 by 4. So we got here 0.0855. This is the pole pitch, and net iron length. That the stacking factor we chosen like a 0.95. So we will get 0.070. That is nothing but 71 mm. 71 mm. So there are 36 slots in the stator that we already considered. So stator slot pitch, that is nothing but pi d by ss, pi into 109 by 36, 9.52 mm we got it. Yeah, and let's calculate flux per pole. This is one of the main parameter. So width of stator tooth, this is already 4 mm from that already existing template. Let's take flux density in a stator teeth as 1.1. So let's calculate flux now. Flux is nothing but BA, flux density into area. Flux density we chosen like 1.1. The area is nothing but 36. 36 is the total stator slots, and number of poles 4. 36 by 4 will give per pole total slots, and each slot width is 4 into 10 power minus 3, and this is the pole pitch for us. So we got 2.82 milliweber is the flux now. So let's check it whether this flux is okay or not. So this is the green color one, the red color one is the inside, that one is the rotor, and this one is the stator now. So the flux pattern is like this. You can see it here. So 4 loops are there. Outer diameter of stator lamination is nothing but D0, 7.125 inch, and that is 181 mm, and depth of stator is 0.75, that is 19 mm, and the depth of stator core DSC, we can use this formula, and we will get this value as 17 mm. Now let's calculate flux density in a stator core. That is nothing but flux density is nothing but flux by area. Here area 2 into Li into dCs. So we got 1.12 Weber per meter square. This is good, well within limit. Up to 2.2, that is the final value, but we should allow for overflux, and stator teeth also is not, thickness also, width also not uniform, so we should consider almost a lower value. Yeah. So stator winding. Next we are with the stator winding. How to design stator winding? The number of stator slots we have chosen is 36, that is the standard number, and slots per pole are so 36 by 4. So we will get 9 slots per pole. Say 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is one pole. So this many slots we have under one pole. Yeah. Generally, the slots per pole can be 9 to 12. Winding factor for main winding. So let's take winding factor as a 0.8. Generally it can be 0.75 to 0.85, and induced EMF So let's consider 5% for a drop. So our remaining voltage is 95%. So 95% of 230 volts. So 219 volts is getting induced. So let's calculate a number of series turns in main winding. Number of turns, how much is required. So that is nothing but Tm E by 4.44 and kWmf into 5m. Here the voltage is 219 volts and 4.44, and we have 0.8 is the winding factor, distribution factor, and we have 50 Hz frequency, and 2.72 is the flux, and this is in milliwebers. So turns in series per pole is nothing but 457. This is the turns. So we have 4 poles, so 457 by 4 is nothing but 114. So we got usually 3 or more coils per pole, each having same or different number of turns. So here we have the turns in each coil, the 4 to 6, 3 to 7, 2 to 8, and 1 to 9. So here you can see coil 1 to 9. So this is the 1, and this is the say this is the 9. One coil 1 to 9 will span of 8 slots. 2 to 8 it will span for 6 slots. 3 to 7 4 slots. 4 to 6 2 slots. So let's calculate sine of 2 by 9, 4 by 9, 6 by 9, 8 by 9, like that. Multiply with the 90 degree, because under one pole it is of 90 degree only. So you got these values. So if add everything, it is coming 2.836, and consider percentage of everything. So 12%, 22%, 30%, 34%, like that. So let's calculate the turns now. So whatever total turns under one pole is there, 114. Among 114, so there is a different consideration again. So 14 turns, 26 turns, and 35 turns, and 39 turns. Total is 114. Yeah. So distance between the distribution of turns in main winding. This is the distribution of turns, how turns were distributed. You can see here. So one turn, one slot we left it here. That is for consideration of auxiliary winding, let's say. So we have 14 turns, 26 turns, 35 turns, and 39 turns. That is the consideration now. So total turns in series for main winding is 4 into 114, that is 456. So there should be like a multiple of number of poles. Yeah, let's calculate conductor size now. For conductor size, we need a current, how much current the winding has to carry. So here 370 watts divided by, so you have 230 volts and 0.65, that is the efficiency, and 0.62 power factor. So the current is 4.07 ampere. This much current will flow in the circuit. So assume current density of 5. Generally 3 to 5 we can choose. Let's choose 5 current density. So area of main winding is nothing but 4.07 by 5. So we got a 0.815. For this 0.815 mm square, standard size is a 19 standard wire gauge. You can just check standard wire gauge in wiki itself, Wikipedia. So this is a 19. So this is the slot dimensions actually for that standard stator frame. So 0.719 is the height, 031 this is the this figure, 091 this is the this figure, and 122 this is radius here, 161 radius at the edge. So area of main winding conductor for this standard wire gauge, main area is a 0.811, and diameter of bare conductor, that is 1.02 mm, and let's take covering of 063.063. So the covered conductor is nothing but 1.083 mm. Generally, space occupied per pole, 70% is by main winding and 30% by auxiliary or starting winding. And here the area of slot, so the area of slot is nothing but 0.189 square inch. So the entire area, that is 0.189 square inch. So that is nothing but 121.5 mm square. And the largest number of turns we have is 39. 39 is the maximum number of turns per slot. So let's calculate area for this 39. So we got 36 mm square. That is the area we need. So let's calculate the space factor now. So 36 mm square area, that's what the conductor occupied, but the total area, available area is 121. This is a 0.296. It means still we have more space now. I mean, more space for insulation, more space for empty space, more space to wind easily. This should be generally less than 0.5. If it is less than 0.5 means it is okay. The winders can easily wind the windings. They can easily make the starter windings. Otherwise, it is very difficult for them. They have to try a lot with the hammer. They have to insert all the installations very hardly. That is very difficult. So manpower is very high cost. Yeah. So here let's calculate length of main turn. We have basic formula here, 8.4 into d plus dss by ss into slot span plus 2l. So this way we can calculate all the for all the turns, for all the slots actually. So let's consider mean length actually. So 14 turns are there, they are of 0.21, and 26 turns are there, they are of 0.27, 35 turns are there, 0.33. So finally we got 0.321, that is the mean length for us. So let's go to the rotor and design the rotor also. So what is the, before rotor we have some air gap, right? What is the length of air gap? That length of air gap is nothing but Lg. Generally we will say over 7 rotor diameter by root 5. This is one basic formula we have. So I'm just spelling 0 also as O, over 7 and 109 by root 4. So this is the number of poles, not pi, number of poles. So we got 0.38 mm, very less, right? So let's take it as a 0.32 mm. So we have a rotor diameter of 109 into 109 minus 2 into 0.32, 108.36. And this is the rotor dimensions here, you can see. So this is the 0.032 and 0.145, 0.3 inch. This is the rotor actually. Number of rotor slots. Per the standard template or standard frame, we have a number of rotors as 44. So this number is this number should be two times I mean pair of poles, whatever pair of poles we have, that is 8. It is more than 8, 36 plus 8. So this gives a good operation actually. And rotor bars. Now let's calculate area of each rotor bar. So we have 0.3 and 0.145, so 28 mm square. Allowing for rounding of corners and all, let's consider area as 20 mm square. The area of rotor, that is nothing but SR into AB. We have 44 slots, each with 20. So we got 880 mm square. That is what the conductor area we are considering. The area of conductor in main winding, that is nothing but 2 times the turns, right? So 2 into 456 into 0.811, that is 740. So here the factor is 1.19. I mean area of rotor and AR by AM in main winding. Yeah, so this is good. So generally rotor will have more copper area when compared to the main winding starter copper area. Okay, here I have some end rings concept. So this is the end ring, and we have a number of bars here. Current is flowing in one direction, under one pole, another direction, and another pole, north pole and south pole. This is the current loops. That's what actually flowing. So the EMF current in bars and current in end ring. The end ring is a little bit different. So here I derived one basic formula here. Current in end ring is nothing but bars per pole into current per bar by 2. So here you can just go through this. Finally the 0.32 into AR by P, this is the formula we have. So area of a end ring 0.32 into AR by P, that is 70.5 mm square. End ring thickness we assumed as 10 and 7, so 70 mm square area. Let's calculate outer diameter of end ring, inner diameter of end ring, mean diameter of end ring. So we have a gap contraction factor. So the slot opening, we have some basic formulas here. The slot opening is 2.29 mm and slot opening to gap length, this is 7.15. We have one Carter's coefficient that will gives the air gap related parameter for us. So for open slots, for a parameter of this ratio, here we got the ratio as a 7.15. For 7.15, the Carter coefficient is 0.7. So gap contraction factor we can calculate here, kgss 9.52 by 9.52 minus 0.7 into 2.29, that is 1.2. And similarly, the rotor slots are closed, but the leakage permeance can't be taken as infinite because of saturation. The rotor slots are considered to have an opening of at least 1 mm. We consider like 1 mm opening. There are rotor slot opening 1 mm. So 1 mm by 0.32, that is a 3.13. Carter coefficient for 3.13 is a 0.47. And let's calculate rotor slot pitch also, YSR. So pi into 108.24 by 44 slots. So almost we got 7.73 mm. Here gap contraction factor is 1.28 now finally. So let's calculate a saturation factor, that is generally assumed as 1.15 in. So let's calculate the resistance of main winding, that is rho L by A. Rho here is a 0.021. We have 456 turns and each of 0.321 length, and area is 0.811. So we got 3.06 ohms. This is at 75 degrees centigrade, and similarly we can calculate for 20 degree also, because that's what we will measure generally. And let's calculate resistance of rotor also. So this is the rotor of length L, and so generally rotor is skewed a bit by 1 turn. So let's calculate rotor length also. Even though it is 75, but as it is skewed by 1 slot 9.52 mm, it is of 75.6. So here also let's calculate ratio. We have one ring coefficient ratio, K ring we will say. So this, from this graph we can get that value. So finally the resistance of rotor referred to main winding. This is one basic formula. So in a separate video I will explain how we got this formula. So rotor resistance referred to stator side, main side. So that is 8 Tm square kW m square P into LB by SR AB plus 2 by pi into dE by P square AE K ring. This is the one basic formula. We got this value at 3.1 ohms, and the resistance at 20 degrees centigrade we can just convert it. So let's calculate reactance also. This reactance also plays a major role. So this is the slot actually. So there are different parameters A1, C, B and E, and so these are different parameters. So this portion is generally taken as a tapered C portion. So here we are calculating so many parameters, ratio B by A2, and from this graph we got 0.8 F value. Specific fermions for stator slots, we have this basic formula lambda SS mu naught F plus D by E plus 2C by E plus A1. This is one basic formula. So finally we got 1.875 mu naught. And specific fermions for rotor slots also we can calculate in the similar way. So here this is also another formula we have. This is a basic formula. So arbitrary correction factor, we are calculating one factor Cx here, and Cx is a 0.96 for us. And slot leakage reactance in terms of main winding, finally we got XS as 2.8 ohms. Similarly we can calculate zigzag leakage reactance and overhang leakage reactance and magnetizing leakage reactance and skew leakage reactance, and by calculating all the leakage reactances, finally we can calculate total leakage reactance referred to main winding. So the main winding XLM, that is XS, XZ, X0, XK. So 6.75 ohm, that is what final value we got. Let's calculate the ratio R by X, 3.1 by 6.75, this is 0.46. And open circuit reactance, that is nothing but we will just take off the leakage reactance. So that is 147.4, and the leakage factor we got it as 0.976, KR and KI. Now we almost finished that leakage aspect. Now this is of 0.5 mm core, and let's calculate the weight of stator steel. This is basic equation. We got 1 kg, and flux density is 1.725 flux density. Even though 1.1 is the average one, the maximum flux density is 1.725. So loss per kg is 11 watts. So iron loss in a stator teeth we got as 16.5 watts. Let's calculate the mean diameter of stator. So we got 0.164 m. Weight of stator core also we got it 4.73 kg, and flux density in core. So this is as per graph 3.6 watts. So total we got 17.2 watts. So 17.2 plus 11, so 28.2 watts. That is the iron loss. Generally we will take 2.2 times the above loss, because rotor has a closed slots, owing to which there is a considerable surface loss. Yeah, so friction and windage loss we assumed as 15 watts. Yeah, this is about different calculation, guys. There is still a lot of parameters calculation, the inrush inrush current calculation, starting current calculation, torque calculation, and circuit diagrams, and starting winding calculation, because we left some space for it. There are some different parameters. Yeah, all the things we will discuss in a next session. Yeah, if you have any questions, comments, or anything, then please comment in comment section. Yeah, if you have any doubts or anything, yeah, subscribe to this channel, don't forget it, so that whenever I'm uploading videos you will get the notifications. Yeah, okay guys, thank you, thanks for watching. We will meet in next video. Bye.